of like scaling, speed optimization, and all the things that are relevant to these models, especially to really large models, so that you can truly focus on building amazing products, build on search, build on recommendation, clustering, text generation, and you do not have to take care of all the hassles you have when you want to train these models or serve these really large models. So today, I'm happy to talk about search. There's like a lot of different terms. Sometimes people call it semantic search. Sometimes people call it neural search. It's a bit ambiguous, what's the term? But first, why all the hype? So here's a real example on the Wikipedia, the simple version of Wikipedia. It has roughly 170,000 documents. And when you pose a really simple search query, what's the capital of the United States? And you use classical lexical search, BM25. So that's what you always used with Elasticsearch for the past 20 years, or with Lucene or Solr. You get the following results for this really simple query. So the first result is on capital punishment, because it talks about capital, it talks about United States. Second entry you get from Elasticsearch is about Ohio, because Ohio is a state in the United States and it has a capital. And the third entry is about Nevada, because it's also a state in the United States and it has a capital. So from a lexical overlap, these are the best results because they contain capital, they contain United, they contain states. But from a user perspective, these hits are completely useless, and you as a user are extremely frustrated. So if you switch to neural search and you use a neural network to retrieve these results, then you get a perfect search result. So the first entry is about Washington, D.C. That's the capital of the United States. Second entry is a definition. So what is a capital city or a capital town? And the third entry is about the United States Capitol, because maybe you as a user, you misspelled capital with Capitol, and you were actually looking for what is the capital of the United States. So neural search provides you much, much better search results. And this is like, as mentioned, like a really unique point in time. So Google solved search by using other signals. So they did not use the signal from the text itself, but in the beginning they used PageRank to know which documents are relevant and important. Then later they used click rates from 100 million of users. But in many, many search applications, you don't have PageRank and you also don't have 100 million of users. So if I wanted to build like a really good search function for my inbox, for my email inbox, I don't have PageRank, I don't have 100 million of users, so I'm left with these really shitty search experience from lexical search, which never works and gets everyone frustrated. And now finally with neural search, we see so much better results. You cannot only put this with like some cherry-picked example, but you can also put like numbers to it. So here's a benchmark from 2004, so the track organized by NIST, organizing search benchmarks since a long time ago. And in 2004, they put out the robust 04 benchmark, and the black line is like the best system from 2004. And then you see here the performance up to like 2018. So like over 14 years, there was like basically no improvement. And systems in 2018 were as good as systems in 2004. So what changed then in 2019 is the pre-trained transformers, so specifically BERT. And we saw in 2019, 2020, a lot better results. And this continues also in 21 and 22. So we really saw a big steep of improvement in terms of search results, which we have not experienced for 20 years before. So this is not only like an academic benchmarks, also the big search engines, they quickly adapted this neural methods. So Google in 2009, they put out like an update to the search engine. And before it has issues you have in lexical search. So when you search for like Brazil traveler to US need a visa, the original Google gave you the information if a US citizen can travel to Brazil without a visa. But the user wanted the opposite, that a Brazilian traveler does this person need a visa when go to the US? And with the update, you get the correct results from the Brazilian or from the US embassy in Brazil about visa restrictions for Brazilians who want to go to the US. And Google, they say it's the biggest leap forward in the past 5 years and one of the biggest leap forward in the history of search. And Google was not only the only one making this conclusion. So Bing also rolled out in 2009, included neural networks into the search function of Bing. And they say it delivers the largest quality of improvements to our Bing customers in the past year. And as mentioned, it's not only limited to Bing and Google, where you have millions, billions of users, but now you can use it without large customer bases, user bases, which makes it extremely friendly for any startup who wants to build like an amazing search function for different applications and scenarios. A challenge with neural networks in search is the hardware need. So this is from Bing, where they rolled out the BERT, a 3-layer BERT layer into Bing search. Said, okay, the original implementation on CPU took like 77 milliseconds, which is like far too slow. So you don't want to wait like 80 milliseconds to get your search results. Also, it would have cost like 10,000 of servers to be added to the search function. So what Bing did is then to use like optimized GPU instances and also optimized Azure further to work with GPUs. So they were able to bring it down from 77 milliseconds to just 6 milliseconds and to use the neural network in the search function, which make it really feasible to deploy it to millions, 100 millions of users. So today I want to talk about different architectures. So neural search is not one solution where you say, okay, this is the one solution you can always use or which always fits. But in fact, there are like many, many different architectures, how you can use transformer networks to improve search results. And it's quite interesting to know what are the pros and cons of these different architectures. And when can you use what and how can you combine them to get the best of like every possible architecture. There are many more architectures, but today I want to focus on Dr. Query, on cross-encoders, and on bi-encoders, and then talk a bit more about how they work, how you can use them, and how you can combine strengths of these individual architectures. I would say these are the most prominent and most common architectures. But as mentioned, there are many more architectures who have certain trade-offs. So simple architecture is Dr. Query, which has like a really nice idea. So it's based on an encoder-decoder architecture. So you take as an input your document, and then you pass this document to your encoder-decoder neural network, and it predicts what are the queries people could ask about this document. So you start with the document. Researchers are finding that cinnamon reduces blood sugar levels. And then the model says, okay, a possible search query could be, does cinnamon lower blood sugar? And you predict a lot of these queries using the model. And then you do a simple concatenation. So you take the original document, you take all the queries you predicted, and you index it in the existing search engine like Lucene, Solr, Elasticsearch. And then when a user query comes, you search through the original document and the predicted queries, and you get better retrieved documents. So it's an extremely simple, nice approach, extremely simple to deploy because you do not need to change the search engine, which you are currently using with lexical search. And the first question is like, why does Dr. Query work? First, it creates better word weights. So an issue with lexical search is that the term frequency is not always the best estimator how relevant a term is. So for example, from Wikipedia, you have a passage, Elon Musk is an investor. He's the founder of SpaceX. He also founded Tesla and the Boring Company with an estimated net worth of he's the wealthiest person in the world. So if you check BM25 TF-IDF, the term frequency for Elon Musk is 1. So it only appears 1. So it's not really important word according to BM25. And so it will not be really retrieved if you search for Elon Musk. In contrast, Dr. Query predicts queries like, who is Elon Musk? What's the net worth of Elon Musk? Which companies were founded by Elon Musk? So relevant terms like Elon Musk get a much higher word weight. So the network helps lexical search BM25 to say which words and phrases are relevant. And it also helps to add new words. So for example, you have a document, July is the hottest month in Washington, D.C., while the coldest month is January. Then a possible query generated by the model is climate Washington, D.C. So here it adds climate to the document, even such that climate is not mentioned in the document itself. And then people analyzed like how much improvement do you get and what helps. So what we see, MRR is the quality, so how good is it? And recall is like how many of the relevant results do you fetch. We see that word weights improves a lot the quality, and in recall it does not change so much. The new words which are added to a document help in terms of the recall, but they leave the quality untouched. And if you combine it and say, okay, you used like the new words and the new weights from Dr. Query, you get like big boost, like 10-point boost in terms of quality, and you got also 10-point boost in terms of recall, which is a really significant improvement. So where every user will directly see, okay, this search function got a lot better. And it's really easy and simple and straightforward to implement because you don't need to change anything in your search engine. You just generate this query and you index them with your original document into your search engine. Second architecture I want to talk about is cross-encoders. So cross-encoders is a re-ranking algorithm. So in search, you often use like a two-stage approach. You have your search query, and then in the first stage retrieval, you go from all the documents you have, possibly like 100 million of documents, to like a small set of 100, 1,000 documents. And these smaller set of 1,000 documents are passed to the cross-encoder to re-rank them to give you the final top 10 hits you want to show to the user. And the cross-encoder is an architecture you can use for re-ranking. It works in the following way. So you concatenate the query and the document in a transformer BERT network. So you take the query, you add the separator token, and then you take the document. And then in the transformer network, you do a forward pass through all the layers. And then at the end, you take the output from the CLS token and you add a projection that gives you a score between 0 and 1, indicating how relevant is the document for the query. And you do this for all 1,000 documents you got from the first stage retrieval. So you take all the 1,000 documents you got here, you concatenate them with the query, you do a forward pass, and then you get for each query document pair a score between 0 and 1. How relevant is the document for the query? And then you can show the top 10 results to the user. The last architecture I want to talk about are biencoders. So biencoders are extremely popular in industry settings because they have like really nice properties in terms of runtime. But I will talk about some weaknesses they also have in terms of quality. So biencoders, they work with vector spaces. So you take all the documents, you encode them in a vector space, and then when a query comes, for example, the user searches for what is the capital of the United States, you also encode this in the vector space, and then you check in the vector space what's the closest document. So for example, Washington, D.C. is the capital of the United States. And then you return the closest top 10 closest documents to the query to the user. And in terms of architecture, you have the query and the document. And compared to a cross-encoder, you don't concatenate them, but you have them independently, separately. You pass them separately through your transformer network like BERT. You have some pooling operation, for example, a mean of all the output tokens from BERT to give you a fixed sized vector. And then you have some distance or similarity function like cosine similarity, which gives you the score between the query and the document. Often people refer to these also as semantic search when you work in dense vector spaces. So often when people talk about semantic search, they mean this vector space, a dense vector space. And neural search, people often also say, okay, a bit more inclusive to also include other architectures like the cross encoder or Dr. Query, or one of the many other architectures that exist. Nice property of these vector spaces is that it also works across modalities and across languages. So you can, for example, encode all the images you have. So maybe from your platform, you have 100 million of images. You encode them in a vector space, and then someone enters like 2 dogs in the snow as a query. You also encode it in the same vector space, and then you check for the image that's the closest, and you retrieve this image to the user. And you no longer need to add keywords or description or an alt text to your image, so it can directly see from the image what's in the image, and you have a search function on the image without the hassle to add like all this meta information. And it also works across languages, so it doesn't matter if you search for these 2 dogs in English, in German, in Chinese, and Japanese. So it doesn't matter what language you use, so you quickly get a search function for images which does not require any meta information for the images in hundreds of languages using these vector spaces. And the bioencoders, they have like many nice properties compared to lexical search. First, they can overcome the lexical gap. So if you do lexical search and you search for United States, but the document talks about US, it will not find it. So United States and US will not match. Similarly, when you search for US, it will not necessarily know if you talk about US, United States, or us. And these bioencoders, they know, okay, US, USA, and United States, that's all the same. And lowercase US for us is something different than the uppercase abbreviation US. Can also respect the word order. So as shown, the old Google function was not able to know if you want a visa, if you go from Germany to Canada, or if you want to visa from Canada to Germany. So lexical search is not able to differentiate between these 2 search queries. Bioencoders, they are able to do that. And it also knows about related terms. So maybe you search for Spearman correlation in NumPy, but there's no function in NumPy to compute the Spearman correlation, but there's a function in SciPy. And the model knows that NumPy and SciPy are really similar frameworks, can often be easily used interchangeably. So it finds you the entry how to compute the Spearman correlation in SciPy. So these large vector spaces are commonly used in industry. And one challenge is how can you search in large vector spaces? For us as a human, when we see the query, it's like kind of easy to say, okay, these are like the 5 closest points. But for a computer, it's a lot more challenging to go in a high dimensional vector space. Often these have like 700 or 500 to 1000 dimensions to say in 1000 dimensions, what are the top 10 closest points. And there's like a full industry how you can do the search in it with many frameworks, vendors, and so on. One option is to use brute force. So you take the query, you compute the distance to all the documents you have in the vector space, and then you sort it based on the document to find the top 10 closest documents. And the challenge here is, of course, that the runtime grows linear with the number of vectors. So if you have like 1 million vectors, you have a query time up to like 12,000 milliseconds. So often it's only suitable when you have like 1,000 to 100,000 vectors, then the latency is okay. But once you go more than 100,000 vectors, more than 100,000 documents, you need to go to which is called approximate nearest neighbor. There are 2 architectures which are quite commonly used for approximate nearest neighbor. The first one is called IVF. So IVF has the idea you take the vector space and you compute like k-means clustering. So as you know it from sklearn, so you create all these cells with k-means clustering. And then when the query arrives, you check in which cell is it, so in which cluster is it. And then you just search in this cluster for the closest neighbors. Or you can set also that it not only checks this one cluster, but also neighboring clusters. to find close points to this query. Third approach to find relevant documents quickly in large vector databases is hierarchical navigational HNSW. I sadly forgot what's small world. Hierarchical navigable small world algorithm, which is also really, really popular approach. So here you use a hierarchical graph. So you have some starting point of your query. And then in the topmost layer, you have like really large steps, and you look for, okay, which nodes is like close to the query vector. So this is like the closest one to this specific point. And then the next one is a more fine-grained mesh, like more fine-grained graph. And then the next layer is the most fine-grained layer. And then you find like, okay, what's the closest point to your starting point? So the top layer makes like really large jumps in your vector space. And then the more deeper you go in the layers, the more fine-grained are the jumps, and the more closer you go to find the closest neighbors to your query. And as usual, there's like many trade-offs, and it's a science for itself how to pick an approximate nearest neighbor algorithm. First, in terms of quality, so how good should be the recall? So do you really find the top 10 closest entries, or does it maybe not find all of the top 10 closest entry? How much memory does it consume? So some approaches like HMSW requires a lot of memory. How many queries per second do you want to process? Do you need to process like, I don't know, 10 queries per second or 1 million queries per second? And finally, how long does it take to build the index? And as mentioned, it's a trade-off. So there are methods which are extremely good on quality and extremely good on queries per second, but they're bad in terms of memory, and they take really long to build the index, and vice versa. So there are models which are good on memory, but they are bad on quality. And so you really need to pick the right algorithm for your specific application, and need to see what trade-offs do you want to do. Luckily, there are many vector databases available, from Face, which is like a really raw Python library from Facebook, to, for example, Pinecone, which is a managed solution, and everything in between. And this helps significantly to index like large vector spaces with 100 million of entries, and to do efficiently search in these vector spaces. So my focus in general is more how to train these representation models. So I less focus on how can I find efficiently the closest neighbors in the vector space, but how can I train really good models to create really nice vector spaces so that I can search for images, that I can search for text, and find really relevant hits for my query. So one approach people use here is which I call multiple negative ranking loss. Sometimes people call it also training with in-batch negatives, or info NCE, or anti-cross entropy loss. And the idea in general is that you have like positive pairs. Positive pairs can be, for example, you have a query and you have some answer, or it can be in a social forum, it can be a question and a duplicate question, or in a citation graph, it can be a paper title and a cited paper title. And what we want is that AI and PI, so A1 and P1, should be close in the vector space, and for all others, it should be distant in the vector space. So here, A1 and P1, so the query, the question, and the answer should be close in the vector space, and all the others should be distant. So the A stands for anchor, and the P stands for positive. So an intuitive explanation would be the following. So for example, as an anchor, we have how many people live in Berlin, and then we have like different positives, so different P's. So the first P, the matching P, is around 3.5 million people live in Berlin. And then we have different other text. Washington, D.C. is the capital of the US, and the 21 Olympics are held in Japan. And what we do is we compute the embeddings for A1 and P1. Then we compute the similarity between A1 and P1, P2, and P3. And this is our prediction. So we say A1 and P1 has a similarity of 0.5, 0.3, and 0.1. And as guild label, we say A1 and P1 should be close, should have a really high similarity, and the other should have like a really low 0 similarity. And then we can just use the cross entropy laws and do backpropagation and update our models so that A1 and P1 are close in the vector space, and all the other P's are distant in the vector space. So you don't do this with like one question and 3 candidates, but you have always these pairs in a batch. So you have like question and answer, question and answer, question and answer. And then you compute all the embeddings for all the questions and all the answers. And you compute all the possible similarities between all pairs of all questions and answers. And you see it as a classification task where you say A1 should match with P1, so it should be close with P1. A2 should be close with P2, and A3 should be close with P3. So this is like you have ones on the diagonal, and then you can just train it with standard cross entropy laws like any classification model. So a really simple way to make your model better is to use larger batch sizes. So here's a paper from Rocket QA where you see on the x-axis the number on the batch size, and on the y-axis the quality. And the black one is like the quality of the model. And as you go from a batch size of 128 to 8,000, you get a constant improvement. So it's the most simple way how you can make it better is to increase the batch size. However, the issue is the larger the batch size, the more GPU memory you need. And at some point, you often need to use multiple GPUs, maybe multiple GPU servers to train really with these large batches. And the other option to make it better is to use with hard negatives. So this is the red line. So we see a nice jump in performance if we go without hard negatives to train with hard negatives. And this is a hard negative for A1. So the N's, they should be similar to the P, but they should not match with A. So good example how it would look like would be how many people live in London, and the positive would be around 9 million people live in London, and the negative, the hard negative, would be around 1 million people live in Birmingham, second to London. A bad example for such a triplet would be if the negative is London has a population of 9 million people, because then we try to tell the model that A and P should be close, and A and N should be distant in the vector space, which does not, from a human perspective, doesn't really make sense that A and P in this example, in this bad example, should be close and A and N should be distant. So here the quality, what you select as the negative, as the hard negative, makes an extremely important role. It has to be really hard for the model to decide is P or N the correct answer, but it cannot be another valid answer to the question. So how can you find these hard negatives? So one strategy is you exploit the structure in your data. For example, you have a citation graph, you have a title, and then this paper cites some other paper, and the cited paper cites some other paper. And you say, okay, 1 hop in the citation graph is more relevant than 2 hops in the citation graph. So you use this as a triplet. Another option is when you go in online communities, you have like maybe some upvotes, and you know, okay, this question got an answer which has like many stars on, for example, Stack Overflow, and another answer with fewer stars. So you say, okay, this question should be closer to the answer which got like a lot of stars, a lot of upvotes, a lot of likes, whatever, compared to the other answer which got like few stars, upvotes, likes. And strategy 2, if you're missing such structure in your data, is to mine hard negatives. So you can use BM25 or some other retrieval technique to find the top 100 most similar text to the anchor. And then you can select one of these randomly. But here it's a challenge. So if lexical search works really good, you often get negatives which are not negatives, so which are other valid answers to the anchor, to the question. And this really hurts the performance of the model. So there's a lot of research and science going in how you can get good hard negatives because they significantly improve the quality of your model. So a big challenge is to transfer embedding models to new domains. So if you're Google and you have 1 billion users clicking on stuff and searching, you get like an infinite number of training data. But if you're a startup, if you're a developer and you go to some new domain, for example, you go to the legal domain in the pet food industry, you hardly find any training data for this, labeled training data for this. And also often, I mean, we're lazy. We don't want to create like large training data sets. So we want to use models out of the box, which are provided, which are pre-trained, and use them for our really specific use case. And a challenge with dense bioencoders is the curse of the unknown. So if you take a new word, for example, big bird Pegasus, so big bird Pegasus is a special type of transformer architectures, and you encode them in a dense vector space, the model has to put this word, which has never seen this word, somewhere in the vector space. So is it similar to bathroom? Was it similar to drill or sprinkler? And the most similar words are actually big boss, big data, and big S. So it's a kind of really bad representation of the word. So if you search for big bird Pegasus, it might be that you find some documents talking about big data, which is not really connected to what you're searching for. And the big question is like, how do these bioencoders handle unknown words? So words which were not seen during pre-training, or words which were not seen during fine-tuning, this constructive training with the triplets. And where do you put these words in a vector space? So big bird Pegasus is some transformer architecture. Klex chain is a cryptocurrency. Forward is an AI startup from Israel. And these OXC004F is an error code connected to the Windows activation key when Windows is not able to verify the activation key. And if you have never seen this, how do you find the right space in the vector space? And dense bioencoders, they try to infer the meaning from the word form, but which is often not really possible. So if you see this error code, you have no idea that this is connected to the activation key of Windows if you just look at the word form. Another big challenge are synonyms and related terms. So how do you know that coronavirus, COVID-19, and SARS-CoV-2 are connected? So especially if you use like an outdated model like BERT, which was trained in 2018 on kind of old data, has no idea about these synonyms. So if you search for coronavirus, it will not find any documents talking about COVID-19 or SARS-CoV-2. And similar new acronyms like which vision transformer model is the best, and then you have the answer, VIT has been doing great in our experiments. So out of the box, the model does not know that VIT stands for vision transformer. So these are really, really big challenges when you use these dense models. And we wanted to test it a bit more systematically, see, okay, how do different approaches perform out of the box in different use cases? So last year, we created the BEER, the benchmarking for information retrieval, where we collected a lot of different tasks with many data sets and domains on information retrieval with really different use cases. For example, in tweet retrieval, the query was a news article, and we wanted to find tweets talking about this news event. And then we tested different models, how well they perform. And before that, people were saying, okay, these dense models, they were so great and the performance was really good. And they only showed it like in domain where they had training data. And as you see, if you compare to lexical search with BM25, you get like an 18-point improvement, which is noticeable by any user. However, if you go to a different domain, so if you go to a domain on the biomedical domain or in scientific publications, you often saw that these dense bioencoders perform weaker than lexical search. And in fact, BM25 lexical search was better than these dense bioencoders on 10 out of 18 datasets. And we not only tested dense bioencoders, but we tested a lot of different approaches. So the best performing approach was BM25 for first stage retrieval and then using a cross encoder. Second best approach was doc to query using a T5 model, then people call it doc T5 query. And then other models are, the performance gets worse and worse. So for example, the dense passage retrieval model from Facebook was only doing well on Wikipedia because it was trained on Wikipedia, but on all the other 17 data sets, it was not trained on. It was a lot worse than BM25 lexical search. And yeah, these dense embedding models like TASB and MCDPR, they have issues for unknown domains. But there's some new architectures called sparse embedding models, specifically Splake version 2, which work better for unknown domains. So the authors tested it on 13 data sets, and it was better than lexical search on 12 data sets. In search, you differentiate between interpolation and extrapolation. So interpolation is the train and test set is really similar. So for example, you have a grocery e-commerce store, and every day thousands of people search for milk in some variation, like fat-free milk, fat-reduced milk. And here the train and test set is like really similar. In extrapolation, your train and test set is really dissimilar. So for example, on a news website, you maybe have some training data, but this training data will be outdated in a week because next week people will search for other news events. And what we see for lexical search, obviously, it does not make a difference if if train and test is similar or train and test is dissimilar. For the cross-encoder, it's also extremely robust. So you only have like a really small drop in performance if the train and test set is dissimilar. But for these dense bioencoder, you see like a big drop in performance. So the dense bioencoders, they work nicely when you have a lot of training data, but they don't perform that well if you don't have training data or when the test data is really different from the training data. And we also saw it on our beer benchmark. So in domain, when you have training data, dense model and the cross-encoder are much better than lexical search, and often the performance is really comparable for these two models. But if you switch to the domain to like bioask, biomedical domain, you see a big drop in performance for the dense model, but the cross-encoder model is actually much better than the lexical search. So you could argue, when cross-encoders are so good and so robust, why should I care about bioencoders and vector spaces? And the issue with cross-encoders is that they are slow, extremely slow. So imagine you have a query which has 10 tokens, and you have documents which has like 240 tokens, and you want to re-rank 100 documents. For a bioencoder, it's really simple. You compute the embedding for a query, takes maybe 10 milliseconds for 10 tokens. For a cross-encoder, you concatenate the query with all these 100 documents. So you need to re-rank 100 times 250 token documents. And in transformer architecture, the runtime is quadratic with the length. So encoding or doing a forward pass on a 250 token text is 25 times 25 longer than on a 10 token text for the query. So overall, the cross-encoder requires 60,000 times more compute than a bioencoder. And this, if you think about deployment, you care about latency. So how quick do you get the search results? You also care about deployment costs. And a cross-encoder with 60,000 times higher compute cost and latency is just not feasible if you want to scale it to many search queries as you have it in like web search, social network search, and so on. The other issue with cross-encoders, they require like a first stage retrieval system. So if you use as first stage retrieval lexical search, the cross-encoder can only be as good as a recall from the first stage retrieval system. So if the first system misses relevant documents because people used a synonym or so, the cross-encoder cannot re-rank it to the top. However, as mentioned, there are like now nice ways how you can combine different architectures and adapt it to specific domains. So last year, my PhD student worked also on a nice way how you can adapt these bioencoder to new domains. So as mentioned, bioencoders, they're extremely efficient, really cheap to run, but they perform really poorly on data which they have not seen. In previous method, they did like some pre-training on the target domain. So you did pre-training on the biomedical domain, and then you did fine-tuning on the labeled data you have, for example, from MS Macro, which are queries and relevant, so Q&A pairs from Microsoft Bing. But this approach requires expensive training on the labeled data on MS Macro. And the data sets where we have labeled data gets bigger and bigger. So MS Macro has 500,000. At Cohere, we use like multiple billion Q&A pairs, and would be like really expensive to first pre-train on your target domain and then do fine-tuning on billions of Q&A pairs. So instead, what we want is to take the model we trained once on billions of text pairs and adapt it unsupervised to a specific target domain like the biomedical domain. And here we invented GPL, generative pseudo-labeling, which combines all these architectures together. So you start with query generation, doc to query, you do negative mining, and you do pseudo-labeling with the cross-encoder. So the first step is using doc to query. So as remember, doc to query is also really robust to new domains. And you take all the documents you have, you ask a T5 encoder-decoder architecture to predict different queries. So you have a document about Python as a programming language, and then the model predicts search queries. What is Python? How good is the readability of Python code, which could match to this document. Then the second step is the hard negative mining. So you take a question, which programming language uses indentation? You take your corpus of all your documents and run lexical search or bioencoder search or whatever search you want to find relevant documents that talk about which programming language uses indentation. And then you take the cross-encoder to predict the relevancy. So you combine the query with all the documents you retrieve and predict the relevancy. So here it's not normalized between -0 and 1. It's an unnormalized score. The higher, the more relevant is the document. And so here's a real example how it looks like. So this is from the financial domain. You have a document about futures contracts. Futures contracts are a member of large class of financial assets. Then you ask the doc to query model to generate a query. So it says, okay, what is a future contract? Is a good query for this document. You retrieve from your corpus different negatives, and then you predict from the cross-encoder different scores. And some documents are really negative. So for example, -2 is what the moment you exercise, you must have $5,000 in a margin account to use the futures contract. So this is does not really answer the question, what's a future contract? But here, -3 is a false negative. A futures contract is simply a contract that requires party A to buy a given amount of community from party B. So here, the user would say, yeah, I don't care for this query, positive and -3 would actually be quite relevant. And we see it in the scores. So in this scores from the cross-encoder, we see the positive is really relevant, -3 is really relevant, and -2 has like a really low relevancy. And so based on these scores, we can train then an embedding model that mimics the scores. So it takes the scores from the cross-encoders and tries to put the different pieces, the queries and the documents at the right distance in the vector space. And this gives you a really nice performance boost. So out of the models, we tested it on 6 data sets. We got an average performance of 45. And then using this generative pseudo labeling, we get an improvement of like 6 points. If you add pre-training on the domain, unsupervised pre-training using TSDE or MLE. So TSDE is another pre-training architecture we developed to pre-train specifically for embedding models. You can get another point of improvement. And what's also nice is that the performance increases the more compute budget you have. So you take your model. So here it's the out-of-the-box model. And then the blue is the function where you use this generative pseudo labeling approach. And the longer you train, the better the model gets and gets adapted to your specific domain. Okay, as a conclusion, so neural search methods can make search much better, but it's not necessarily guaranteed. Just because you throw neural search at a search problem does not guarantee that it gets better, but you have to know what are the strengths and weaknesses of different approaches. Do you have training data or not? And if you do not have training data, how can you combine different approaches to get at the end a really good and really fast search function? So there are many different techniques. Today I talked about doc2query, which generates queries given a document. You can either use it directly with an existing search solution like Elasticsearch, or use it to train other models. Cross-encoders, which is a re-ranking method, which concatenates the query and the document and then predicts a single score on this. And biencoders, which projects query and document independently into a dense vector space, and then you can do vector space operations to find the closest neighbors. And challenges in general exist on unseen domain. So how do you know about acronyms and synonyms and concepts on data, on unseen data? So in terms of research, we need promising new techniques for self-learning without labeled data. So how can it learn that Corona and COVID-19 are related? I mean the same thing, and I can present the user the one or the other document. That's so much from my side. Yeah, thanks so much for joining and looking forward to some questions. So if you have some questions, feel free to unmute or write them in the chat.
Great. Thanks, Nils, for the presentation. I see some questions in the chat. Again, for everyone, if you have questions, it's time to send it in the chat. If you prefer to speak to ask questions, you can raise your hand. I can unmute you to speak.
So yeah, maybe I can just check. So probably I will miss some questions in the chat. I will just answer the question I see here. So there was like one question: what could be the reason that BM25 does so much better on out-of-domain data than large language models? So the issue we have with these bioencoder models that you force to put words somewhere in the vector space where it does not really make sense for them to be, especially for like unknown entities. In BM25, it's really easy. So if it sees an unknown word like this error code, so this, like this error code, it does not try to infer what does it mean. It just creates like a new dimension for it. And if you search for this, you find documents containing this, which is like a really good baseline. So if I search for this, give me documents containing this. While these dense bioencoder, they try to infer what's the meaning. And if it has never seen this word, it's not really able to infer the meaning of the word and gives you kind of like garbage results. So there's a question from Adam using two different encoders in a bioencoder setup. So in theory, you could use two different encoders, one encoder for query, one encoder for document. This is done by Facebook and OpenAI to use two different encoders, which does not make sense. So it's mainly done by incompetence by these two parties. So you get much better results if you use the same architecture for query and document, basically, again, because of these unknown words. So if there's an unknown word passed to the same transformer architecture, you hope they get somewhere close in the vector space. The only reason when you want to use two different architectures is when you want to use a document with a large network and you want to use a small network for the query to get like a better latency. But to use two networks of the same size, of the same architectures, but independently trained for query and document does not make really sense. And all studies show that it's much better to use the same network for query and document. So there's a question from SJ. Can you comment on the loss of phrase search in dense vectors and what in hybrid search? So yeah, would you recommend hybrid search, dense vector search, and re-rank using BM25? So there are like many ways how you can improve vector search. So we've seen that this dense embedding approaches, they perform really well when you have training data, but they don't perform well if you don't have training data. Nice approach, which I was not able to discuss today, is hybrid search, where you combine lexical search with embedding search, and then you retrieve one set of documents from BM25 with lexical search, one set of documents from your vector space with approximate nearest neighbor search, and then you combine these two search results, search rankings. And results show that it gets much better and also a lot more robust because there are like pros and cons for lexical search. So lexical search is really good if you want to do a lexical search. So if I care about documents containing this specific phrase, this specific error code, it's impossible to beat lexical search, while embedding search is extremely good in like generalization, topic search, and so on. And then if you combine both, you get both of the best of both worlds. However, in terms of deployment, it can be a challenge because you need to maintain index for lexical search and you need to maintain index for embedding search. And as of now, there's no good vector database which is good at lexical search and good at embedding search. So there's like still many issues. And then, yeah, so SJ is asking, so you can use dense vector plus BM25 plus cross encoder. That would be, in general, the best approach, but you have to be careful in terms of deployment cost and latency, that if you take like really powerful dense vectors plus lexical search plus cross encoder, that the computational cost and latency does not get too high. So from Jury, there's a question, how are GPL scores generated? So they're generated, so these scores are generated from the cross encoder. So we take the query and concatenate it with the document. So what is futures contract? Futures contract are concatenated as a string of input to a transformer network, and then have from the cross encoder the output, how relevant is the document to the query. And here the cross encoder said it has a relevancy of 10, here it says it has a relevancy of 8, and here of 0.3.
Hey, nice. We have one raised hand. Maybe we can take the questions from him. Hey, Ram3, you can speak.
Hi, Nils. Thanks for the talk. So my question is, let's say if you're trying to do classification task on legal or medical documents, so what is the difference between pros and cons between two different approaches? So the first one is you have sentence vectors extracted from, let's say, text, and then you just have a top level classifier on top of that. Second thing is you choose a base BERT model and then either fine tune or directly train a classifier with all the parameters, right? So what are the pros and cons between these?
So the first one is called linear probing, where you take an embedding model and you add like logistic regression classifier on top. So the pros are training time is extremely fast. So you often can train it within like a few seconds. Also, it's really easy to have like multiple classifiers. So maybe one document, you want not to only classify it for one client, but maybe you have like 10 clients, 100 clients, or 100 models, which want to do like different classifications on it. So it's really easy to add like different classification heads on top of it and have it classified. The disadvantage is the accuracy you achieve. So because you just classify on top of the vector space, the accuracy is not the best. If you do fully fine-tuning where you update all the weights from the transformer network, you have better accuracy numbers, but the disadvantage is that the training is slower, and for each classifier you create like a new copy. So if you have one text and you have a lot of different classification tasks, so for example in social media you have like one post I write on Facebook, and then Facebook has like hundreds of classifiers on top of it for spam, abusive content, for ads, for recommendation, and so on. You wouldn't need to have like 100 copies of these large transformer architectures.
Got it. Just a quick follow-up on that. So in the second case, is it better to fine-tune, let's say, BERT or ROBOT first as a language model and then fine-tune the classifier, or how would you recommend?
Yes, so here adaptive pre-training is usually good. So if you work on really specialized domain like legal domain, you take some existing pre-trained model, BERT, ROBERTA, DBERTA, whatever is state of the art. You pre-train it on your target domain using NLM. So you run NLM on legal text, for example, and then you fine-tune it with the classification data you have.
Got it. Thanks a lot. Thanks a lot.
Welcome.
Great. Next question is Avinash from Germany.
Yeah.
Go ahead.
Thanks for the talk. I just have a question regarding, like, I wanted to train a bioencoder, but I also want to utilize metadata such as numerics. For example, I can give you an example, like an apple is my anchor, positive would be the fruit, and I would also include the nutrition values of it, like, for example, it would be 30. And the second sentence would be apple organic, and positive is also a fruit, and the nutrition values is 45. So I would like to include this type of metadata, but I just gave like one example, but is it possible to add like multiple metadatas for an anchor and train the positives?
Yeah.
Especially I was looking for an answer for numerical data. How can I handle it?
Yeah, that's a challenge in general. How do you get like numerical data, categorical data? Also in e-commerce, often you have like popularity of a product. So you search for, I don't know, coffee machine. You not only want to match on like coffee machine, but how popular is the product? Like how good are the reviews? How high are the sales number? And one way is you can sometimes create like a text out of it. So you take your query and then you add like more text to it. So you say, this is my query, or maybe, let's see where. So you take your query text and then you add like just some text to like nutritional value high, or you create like some bins, and then you pass it as an input to your transformer network. So you can, this often works with like category data, like that you say, okay, my document or my query is not only like the text itself, but I append text on categories, on features I have, and pass it through the transformer architecture. Or you can add like a layer on top so that you get from the document the vector, and then you have some features which you concatenate with the vector, and then you have another layer on top which takes as an input your vector and the features, like a linear layer, which then creates the final vector which you use in the vector space. But in this case, you often need to do like need to have training data and backpropagation, so that you learn how important are different features, nutritional value, category data, sales number, popularity, review score. How important is this for the model and for the user decision?
Thank you.
I see we still have quite a few questions in the chat. Maybe we can go with the last one, since we are kind of over time. Okay. Maybe you can just choose the last questions.
Okay. So let me see. Yeah, there are many questions. So yeah, from SJ, there's a question. In my experience, Dr. Query using 2 to 3 epochs seems to be the best for fine-tuning. Is there like any industry standard to determine how many epochs to use for training, such the way that the quality of the model is still good? Yeah, so how long you should train is like a really, yeah, there's like a whole chapter of science to it, how long you should train. First, I would say it depends like on how much data you have. So what we saw when you have like few examples, let's say you have 10 labeled examples, 20 labeled examples, training for more epochs is often really helpful. So you want to do like many epochs over like the few examples you have. The larger the training gets, so if you go to training sets of millions, billions of training pairs, you only do like a single epoch. But there often you have the issue that the model at some point will not be able to learn anymore. So maybe you see the model improves for the first 10,000 training examples, but anything after 10,000 training examples, the model stays flat and does not improve anymore. So it does not learn from more information. And yeah, there can be different reasons to it why it would not be able to learn from more information. One could be that the model capacity is too small. So the smaller the model, the less it can learn and remember. Or it can be due to whatever other reasons. And yeah, it's a big challenge. What's the correct number of training? There's no good solution to it. Often training for 3 epochs works good, so you do nothing wrong training for 3 epochs. And then in edge cases, when you have little data, you want to train for more epochs. When you have a lot of data, you train for 1 epoch and you want to check if the model is actually still learning if you train on more data.
Thank you, Nils. Appreciate it.
Great. Thanks a lot. Yeah, I see still quite a lot of questions in the chat. Unfortunately, we are over times. So maybe, I guess you can connect to the speaker, Nils, to on the LinkedIn or on the Twitter or emails for the follow-up questions. Or if you want to stay in the chat, you can type the chat to answer some questions. Again, thanks a lot. It's great presentations. Let's give him a round of applause. If you can turn on your cameras to send a clap, or you can send a clap in the room chat, or through the room claps.
Great. Yeah, thank you so much. So yeah, slides are shared on my website, Reimers.de. And also I'll link all the talks I give and videos there, so you can find it on my website, on YouTube, and also all the slides. And yeah, feel free to reach out to me if you have questions on search and how to incorporate transformer models into your search use case.